Welcome to Chapter 4, Principles of Flight. In this chapter, we're going to explore the fundamental physical laws that govern how an aircraft behaves in the air. Every time a pilot takes the controls, natural forces are constantly at work, and understanding those forces isn't just academic knowledge, it's essential to safe and effective flying. We'll examine how forces like lift, weight, thrust, and drag interact, how the atmosphere itself plays a critical role in aircraft performance, and how aerodynamic principles determine the way an aircraft responds to pilot inputs. By the end of this chapter, you'll have a solid foundation for understanding not just what an aircraft does, but why it does it. That understanding is what separates a pilot who simply operates an aircraft from one who truly flies it. Let's get started. The atmosphere is the envelope of air that surrounds the Earth, and understanding its structure is foundational to everything we do in aviation. By composition, the atmosphere is made up of approximately 78% nitrogen, 21% oxygen, and the remaining 1% consists of other gases such as argon and helium. What's important to recognize here is that heavier elements like oxygen tend to settle closer to Earth's surface due to gravity. In practical terms, this means that the vast majority of the oxygen available in the atmosphere is found below 35,000 feet, which has direct implications for aircraft performance and human physiology at altitude. Although air is a mixture of gases rather than a solid or liquid, it behaves as a fluid and follows the same physical laws that govern fluid dynamics. It has mass, it has weight, and while it has no definite shape of its own, it conforms to and fills the space around it. This fluid behavior is exactly why principles like pressure, density, and airflow are so critical to understanding how aircraft fly, how weather systems develop, and how your instruments respond to changes in the environment around you. Keep these properties in mind as we move forward. They are the basis for nearly every concept we'll cover in this course. Air behaves as a fluid, and understanding how it flows is fundamental to understanding flight. One of the key properties of any fluid is viscosity, the resistance that fluid has to flowing. Air has very low viscosity, meaning it flows quite easily compared to something like grease or heavy oil, which are high viscosity fluids that resist movement. Gasoline is a good example of a low viscosity fluid, similar in that sense to air. Now, even though air flows easily, friction still plays a significant role. When air moves over a wing surface, even a surface that appears perfectly smooth, at the microscopic level there is enough roughness to slow the airflow down. Air molecules actually adhere to the wing surface itself, and this creates what we call the boundary layer, a thin region of slower-moving air that clings to the wing. When viscosity and friction work together to resist the movement of air over a wing, the combined effect is what we call drag. Drag is one of the four primary forces acting on an aircraft in flight, and it directly opposes forward motion. As a pilot, everything from your aircraft's design to your airspeed management is influenced by the need to understand and overcome drag. Recognizing where drag comes from at this fundamental level will help you make better decisions in the cockpit. When we examine a wing surface under high magnification, in this case 1,500 times, what appears smooth and polished to the naked eye reveals itself to be a complex landscape of peaks and valleys at the microscopic level. This is an important concept to grasp because it fundamentally shapes how air interacts with the wing. Air molecules in contact with this rough surface adhere to it, forming what we call the boundary layer. This thin region of air immediately adjacent to the wing surface is where viscosity and surface roughness combine to create a significant source of drag. The irregularities in the surface impede the smooth flow of air, and the viscous nature of air means that this disruption propagates outward from the surface, affecting the broader airflow around the wing. Understanding and managing boundary layer behavior is not simply an academic exercise. It is a central challenge in wing design and has a direct impact on aircraft performance, fuel efficiency, and handling characteristics. As we move through this course, you will see how engineers apply this knowledge to make informed decisions about surface treatments, wing profiles, and aerodynamic controls. Atmospheric pressure is one of the most fundamental concepts in aviation. and understanding it begins with the standard reference point known as the International Standard Atmosphere, or ICE, established by ICAO. At sea level under standard conditions, temperature is 59 degrees Fahrenheit, or 15 degrees Celsius, and pressure is 29.92 inches of mercury, equivalent to 1,013.2 millibars. These are the baseline values against which all atmospheric measurements are compared. As altitude increases, both pressure and temperature decrease in predictable ways. Pressure drops approximately 1 inch of mercury for every 1,000 feet of altitude, gain up to 10,000 feet, while temperature decreases roughly 2 degrees Celsius per 1,000 feet up to 36,000 feet. A critical reference point to remember is 18,000 feet, where the atmosphere contains only half the weight, and therefore half the pressure, of sea-level air. This matters directly to your instruments. Atmospheric pressure is the driving force behind 4 key flight instruments: the altimeter, the airspeed indicator, the vertical speed indicator, and the manifold pressure gauge. Any deviation from standard pressure conditions will affect these instruments, which is why understanding and correctly applying pressure settings is essential for accurate flight operations. Pressure altitude and density altitude are 2 of the most critical concepts in aviation performance planning, and understanding them can directly affect flight safety. Pressure altitude is the height above the standard datum plane, the theoretical level where atmospheric pressure equals 29.92 inches of mercury. To read pressure altitude, simply set your altimeter's Kollsman window to 29.92. This setting is used when flying at flight levels above 18,000 feet, where all aircraft use a standard reference to maintain separation. Density altitude takes that concept one step further. It's pressure altitude corrected for non-standard temperature. In simple terms, density altitude tells you how the atmosphere is performing relative to standard conditions. High density altitude means the air is thin, and thin air means reduced aircraft performance. 4 factors drive density altitude up: high elevation, low atmospheric pressure, high temperature, and high humidity. The performance impact is significant across 3 areas. First, your engine produces less power because it's taking in less air. Second, your propeller generates less thrust because it's working through less dense air. Third, your wings produce less lift because thin air exerts less aerodynamic force on the airfoils. On a hot summer day at a high-elevation airport, this combination can dramatically increase your takeoff distance and reduce your climb rate. Always calculate density altitude before flight. Pressure, temperature, and humidity are the 3 key factors that affect air density, and understanding how each one works will help you anticipate how your aircraft will perform under different environmental conditions. Starting with pressure, density and pressure are directly proportional. If you double the pressure, you double the density, assuming temperature stays constant. Higher density means more air molecules for your engine and wings to work with, which translates to better performance. Temperature works in the opposite direction. Density and temperature have an inverse relationship. As temperature increases, air expands and becomes less dense. Lower density means higher density altitude, and higher density altitude means reduced engine power, reduced lift, and longer takeoff distances. Humidity is often overlooked, but it matters. Moist air is actually less dense than dry air. This surprises many people, but water vapor is lighter than the nitrogen and oxygen molecules it displaces in the atmosphere. So on a hot, humid day, you're dealing with the combined effects of high temperature and high moisture content, both working against you to increase density altitude and degrade aircraft performance. Never underestimate the impact of humidity, especially during summer operations. Newton's 3 laws of motion form the foundation of everything we understand about how aircraft move through the air, and as a pilot or aviation professional, you need to internalize these principles, not just memorize them. The first law tells us that objects resist changes to their state of motion. For an aircraft, this means that once airborne and moving, inertia wants to keep it moving at the same speed and in the same direction. This is why attitude and power changes don't produce instant results. The aircraft's mass resists those changes. The second law gives us the mathematical relationship between force, mass, and acceleration. A heavier aircraft requires significantly more force to achieve the same acceleration as a lighter one. This directly impacts takeoff performance, climb rates, and maneuvering capability, all critical to flight planning and safety. The third law explains thrust itself. Whether it's a propeller pushing air rearward or a jet engine expelling hot gases, the aircraft moves forward as a direct reaction to that rearward push. Equal force, opposite direction, every time, without exception. These aren't abstract physics concepts. They explain why your aircraft behaves the way it does in every phase of flight, and understanding them will make you a more informed and capable aviator. Bernoulli's principle is a foundational concept in fluid dynamics and aviation. It states that as the velocity of a moving fluid increases, the pressure within that fluid decreases. These two properties, velocity and pressure, have an inverse relationship, and understanding this is essential to understanding how aircraft generate lift. Think about the shape of a wing. The curved upper surface forces air to travel a longer path than air moving underneath. To keep up, that air accelerates, and as it accelerates, its pressure drops. The higher pressure beneath the wing then pushes upward, producing the lift force that gets an aircraft off the ground. The venturi tube gives us a clean, controlled demonstration of this same principle. As air enters the narrowed throat of the tube, it speeds up, just like water moving faster through a pinched hose. That increase in speed causes a measurable drop in pressure right at the throat. Once the airflow passes through and the tube widens again, velocity decreases and pressure recovers. This cycle of constriction, acceleration, pressure drop, expansion, and pressure recovery is Bernoulli's principle in action, and it appears throughout aircraft systems, from carburetors to airspeed indicators. An airfoil is any surface specifically designed to produce a useful aerodynamic reaction as it moves through the air. In the context of a wing, that reaction is lift, and understanding the geometry of an airfoil is the foundation for understanding how both lift and drag are generated. Let's walk through the key terms. The leading edge is the rounded front of the airfoil that faces directly into the oncoming airflow. The trailing edge is the narrow, tapered rear where the upper and lower airflows rejoin. The chord line is an imaginary straight line drawn directly from the leading edge to the trailing edge, and it serves as a reference for measuring angles. The mean camber line runs equidistant between the upper and lower surfaces, and it tells us about the overall curvature of the airfoil. That curvature is called camber, and it's what makes airfoil design so critical. The upper surface is typically more curved than the lower, which causes air to accelerate over the top of the wing. Faster moving air means lower pressure, and that pressure difference is what generates lift. The greater the camber, the more lift produced at a given airspeed, but increased camber also means increased drag. This is why airfoil shape is carefully selected based on the aircraft's intended weight, speed, and mission. No single airfoil design works perfectly for every situation. Not all airfoils are created equal, and understanding the differences between them is essential for any aviator or aerospace professional. The shape of an airfoil is precisely engineered to meet the specific performance demands of the aircraft it serves. The symmetric airfoil has identical upper and lower surfaces, meaning it produces no lift at zero angle of attack. This makes it ideal for aerobatic aircraft and helicopter rotor blades, where equal performance in both directions is required. The cambered or asymmetric airfoil features a more curved upper surface, allowing it to generate lift even at zero angle of attack. This is the most common design found on general aviation aircraft because of its efficiency at lower speeds. The supercritical airfoil uses a flattened upper surface to delay shockwave formation at transonic speeds, significantly reducing wave drag on modern jet airliners. The laminar flow airfoil moves its thickest point further aft, keeping airflow smooth over a greater portion of the wing and reducing skin friction drag. You'll find this design on high-performance sailplanes and select general aviation aircraft. Finally, the NACA numbering system gives engineers and pilots a standardized way to classify these shapes. A NACA 2412, for example, tells you the airfoil has 2% camber, positioned 40% back from the leading edge, with a thickness-to-chord ratio of 12%. Lift is generated through two complementary physical principles working together at all times. Understanding both is essential to understanding how wings actually work. On the upper surface of the airfoil, the curved shape accelerates airflow. As velocity increases, pressure drops. This is Bernoulli's principle in action. The result is a region of low pressure above the wing that essentially pulls the airfoil upward. This suction effect is the dominant component of total lift in most flight conditions. Beneath the wing, the opposite occurs. Air slows as it approaches the leading edge, creating a stagnation point where pressure builds. That higher pressure below, relative to the upper surface, contributes an additional upward force. This effect becomes increasingly significant as the angle of attack increases. Newton's third law provides the third piece of the picture. The airfoil actively deflects air downward, and the equal and opposite reaction to that deflection pushes the wing upward. This flow-turning effect is why even a simple flat surface, like a paper airplane, can generate lift with the right angle of attack. The critical takeaway here is that Bernoulli and Newton are not competing explanations. They are simultaneous, complementary descriptions of the same physical event. A complete understanding of lift requires both. When we talk about how a wing actually generates lift, we need to understand where the resulting aerodynamic force is considered to act. That location is called the center of pressure, or CP. The center of pressure is essentially the average point of all the pressure variations acting across the wing surface at any given angle of attack. Think of it as the single point through which the total aerodynamic force is applied. What makes the CP particularly important is that it moves with changes in angle of attack. As angle of attack increases, the center of pressure migrates forward toward the leading edge. As angle of attack decreases, it moves aft. This movement is not just an academic concept. It directly affects how structural loads are distributed across the wing and has significant implications for aircraft balance and controllability. It's also worth noting that the lift generated by negative pressure on the upper surface is considerably greater than the positive pressure contribution from the lower surface. This means the suction effect above the wing is doing the majority of the work. Understanding CP travel is essential for appreciating why aircraft behave the way they do at varying flight attitudes, and it lays the groundwork for understanding aerodynamic stability, which we'll be building on as we move forward. At the tip of every wing, something unavoidable happens. The high-pressure air beneath the wing doesn't just stay put. It curls upward and around the wingtip toward the lower pressure region above, forming a rotating mass of air we call a tip vortex. This spiraling airflow creates downwash, which effectively tilts the local lift vector rearward, reducing the net upward lift generated by that portion of the wing. The result is increased induced drag and a measurable loss of aerodynamic efficiency. To combat this, designers have developed two primary countermeasures. Winglets, those upturned or downturned extensions you see on most modern aircraft, act essentially as a dam at the tip, disrupting the pressure equalization that would otherwise feed vortex formation. They can be positioned at the top, the bottom, or both. Tapered wingtips take a different approach, gradually reducing the chord length toward the tip to minimize the pressure differential and allow airflow to transition more smoothly around the tip edge. Both solutions target the same root cause, that pressure imbalance at the tip, but through different geometric strategies. Understanding this mechanism is fundamental to appreciating why wing planform design has such a significant impact on overall aircraft performance. This table summarizes the International Civil Aviation Organization standard atmosphere, which serves as the universal baseline for all aircraft instrument calibration. Take a moment to study these values carefully, because understanding the relationship between altitude, pressure, and temperature is fundamental to interpreting your flight instruments correctly. Notice two key patterns in this data. First, temperature decreases at approximately 2 degrees Celsius for every 1,000 feet of altitude gain, up to 36,000 feet. This rate is known as the standard lapse rate. Second, pressure decreases at roughly 1 inch of mercury per 1,000 feet, but only up to about 10,000 feet. Above that, the rate of pressure decrease slows considerably. At sea level, standard conditions are 29.92 inches of mercury and 15 degrees Celsius. These are the benchmark values your altimeter, airspeed indicator, and vertical speed indicator are all designed around. When actual atmospheric conditions differ from these standards, instrument readings will deviate from true values. That is precisely why understanding density altitude, pressure altitude, and temperature corrections matters so much in practical flight operations. Whenever you hear the term standard atmosphere, these are the specific values being referenced. Let's bring together the key concepts from this chapter. First, understanding atmosphere and pressure is foundational to everything else. Standard sea level conditions are 29.92 inches of mercury and 15 degrees Celsius, and both pressure and temperature decrease as altitude increases. All your instruments are calibrated to these ISO standards, so recognizing deviations from standard conditions is essential for accurate interpretation. Second, density altitude directly impacts aircraft performance. High temperature, high humidity, and high elevation all reduce air density, which means your aircraft will perform as if it's at a higher altitude than the altimeter indicates. Always account for these factors during pre-flight planning. Third, lift is not produced by a single force. Bernoulli's principle and Newton's third law work simultaneously. Differential pressure above and below the wing combines with downward flow deflection to generate the lift that keeps the aircraft flying. Finally, airfoil shape and angle of attack work together to control lift and drag. As angle of attack increases, the center of pressure moves forward, and tip vortices become more pronounced, reducing efficiency. Winglets are one effective design solution to minimize that loss. For a deeper dive into any of these topics, NASA's Beginner's Guide to Aerodynamics at grc.nasa.gov is an excellent free resource we strongly encourage you to explore.